Hi. Today we're going to be looking at section 2.3a. We're going to be looking at the product and quotient rules, and that's about all we're going to be doing today, is doing the product and quotient rules, okay? So in the last section, we learned that the sum or difference of two functions, all we have to do is add and subtract the derivatives. It's just the sum and difference of the derivatives. Unfortunately, the product quotient of two functions is not as simple as just taking the derivative of one, taking the derivative of the other, and multiplying. Instead, we're going to use what's called the product rule. If f and g are differentiable functions, then the derivative of f of x times g of x is going to be f of x times g prime of x plus g of x times f prime of x. So what does that look like? Again, it's the first function times the derivative of the second function plus the second function times the derivative of the first function. Of course, this can then be extended to cover lots of different factors, okay? So products involving two or more factors as well, all right? So let's take a look at this product rule. Example 1 wants us to find d dx of h of x, which is 3x minus 2x squared times 5 plus 4x. Now, it's true that we could multiply these together. That's not too bad, and then we could apply the power rule on that. But let's practice our product rule. So if we take the derivative, again, let's look at our first function, which is 3x minus 2x squared. And then we have the second function, which is like our g of x, 5 plus 4x. So again, we want to take the first function, 3x minus 2x squared, and now we want the derivative of the second. And now we're going to add the second function, 5 plus 4x, times the derivative of the first, 3x minus 2x squared. Okay? So let's find those. So let's start by taking the derivative of that second function. So I have 3x minus 2x squared times the derivative of 5 plus 4x. Based on our work so far, hopefully you guys see that that's just going to be 4. Now I have plus, and now I'm going to take the second function, 5 plus 4x, and now multiply by the derivative of the second. Or sorry, the derivative of the first function. And so the derivative of 3x minus 2x squared would just be 3 minus 2 times 2x to the first, so minus 4x. Okay. Then at this point, we can just distribute, and I get 12x minus 8x squared plus 15. My outer is negative 20. My inner is plus 12x, so minus 8x minus 16x squared. And then I can combine my like terms. So my h prime of x ends up being negative 24x squared plus 4x plus 15. Okay? So let's look at number 2. Y equals x squared times sine of x times cosine of x. Well, really, we've got 3 functions that we're dealing with here. We have x squared, we have sine of x, and we have cosine of x. So if we want to find y prime, that means that we could take x squared times the sine of x, and then times the derivative of cosine of x, and then do the same thing. And then what we can do is we can take x squared and cosine of x and multiply by the derivative of the middle function, sine of x. And then we could take the second function, sine of x, the third function, cosine of x, and then multiply by the derivative of the first function, x squared. Sorry, that was a lot of writing. Oops, here we go. Okay, that's just x squared. So let's find each of those. We've got x squared times sine of x, and now we want the derivative of cosine of x. Remember, the derivative of cosine of x is the opposite of sine of x. Now I've got plus, and I've still got x squared, and I had that cosine of x, but now I want the derivative of the sine of x. The derivative of the sine of x is just positive cosine of x, plus, and then I have the sine of x times the cosine of x times the derivative of x squared, which we know is 2x, right? So I just want, I'm color coding just to show you that when we have three functions present, like all three functions are present in each of the terms, two of the original functions, and then a derivative of the third function. Okay. So let's try to clean each of these terms up. This is going to be negative x squared sine squared x plus x squared cosine squared x, and then plus 2x times sine of x cosine of x. Well, one thing that I see is I see that I can take out an x squared from these. And in particular, and I know usually I would probably take out a negative x squared to make this sine squared x minus cosine squared x. But if I just took out an x squared, that would give me cosine squared x minus sine squared x. Why is that special? That's double angle, isn't it? That's the double angle formula for cosine. Speaking of double angles, sine x cosine x is double angle when that's doubled, right? When we have 2 sine of x cosine of x. And so what I can do is realize that these are double angle formulas. And so that means that my y prime can be written as x squared times the cosine of 2x plus x times the sine of 2x. So again, this turned into cosine 2x. This turns into sine of 2x. So remember that these are utilizing the double angle formulas. All right, now you might say, what's the importance of that? Well, I talked to the BC Calc teacher, who also teaches HL, about that. And she said that the double angle formula, particularly for sine, often shows up on that AP exam, and not necessarily on their free response portion. But if this was a multiple choice question, right, and you got this as your answer, they might have this as the multiple choice answer that they want you to get. And in order to get there, you're going to have to rearrange things and get those double angle formulas. So, and use those double angle formulas to get that. Does that make sense? Okay. And I would try to be specific about what I would be looking for in your final answer in a quiz test situation. So if I said something like, write your final answer with only 2 terms, this would be a nice way to do that, wouldn't it? All right. But if I didn't specify, technically at this point, we've got, I mean, you know, you've got each term, you know, simplified. We don't have any, we can't combine any like terms, etc. So, but again, this is preferred. It's a lot cleaner, isn't it? Looks nice. Again, so problem 1 was a case where h of x could have been revised. And then we wouldn't use the product rule, but we would use the power rule and the sum difference rule. But this was really nice for us to be able to practice the product rule that we just learned. Let's do another one. Example 3 wants us to find the first derivative. And we're taking d dx of x times the sine of x. So that means that I'm going to take x times the derivative of sine of x. And then I'm going to take sine of x times the derivative of x. And the product rule then says that I would add those together. So that means that I would have x times the cosine of x plus the sine of x times the derivative of x, which is 1. So essentially then I would just have x times cosine of x and then plus the sine of x. That looks fine to me. That would be our derivative. What about number 4? Y equals 2x cosine x minus 2 sine of x. We use the product rule anytime there are 2 or more functions involving x. And in our first term, that's what we have. We've got 2x. I mean, you could just think about it as x, but it's not bad with a coefficient. We've got 2x and cosine of x. Those are going to be the 2 functions that we're going to use in the product rule. Here, when we have 2 times the sine of x, the 2 isn't a function of x itself. So here we're just going to use the constant multiple rule. So it is important for us to realize when it's appropriate for us to use the product rule, when we have 2 or more functions involving x, and when we can use the constant multiple rule. Okay, so just be cautious about that. So if I were to take y prime in this case, I would want 2x times the derivative of cosine x, oops, d dx of cosine x, and then plus cosine x times the derivative of 2x. And then notice that here where we use the constant multiple rule, we just want the derivative of this. So we just want 2, and then essentially we'll just take the derivative of sine of x. Sorry about that. That's why we use pencil in real life. All right, so let's do each of those. So this is going to be 2x. Remember, the derivative of cosine of x is the opposite of sine of x. And now we can take the derivative of 2x, which is just 2. Then we have minus 2, and the derivative of sine of x is just cosine of x. So we do want to take the derivative of each term. Just in the first one, we end up having to use the product rule, and in the second one, we just use the constant multiple rule. So this gives me negative 2x sine of x plus 2 cosine x minus 2 cosine x. And we can see that we can combine our like terms, and we end up getting negative 2x times the sine of x, and that would be my derivative. Okay? So again, if you guys know your rules, this isn't too bad. It's just important for us to remember that we can't just take a derivative, and multiply. We want to use each piece. We want to use the first function and then the second function's derivative, and then we want to use the second function and the first function's derivative. All right? So example 5. The reproduction rate F of the fruit fly Drosophila melanogaster, grown in bottles in a laboratory, decreases with the number P of flies in the bottle. A researcher has found the number of offspring per female per day to be approximately F of P equals 34 minus 0.612 P, times p to the negative 0.658. The first thing it asks us to do is to find f of 15, and then it asks us to find f prime of 15. Well, f of 15 sounds pretty easy, right? Let's start there. I'll use blue. So let's find f of 15. So we know that to find f of 15, all we need to do is plug 15 in for p, essentially. So we have 34 minus 0.612 times 15. Let me change that. And then times 15 to the negative 0.658. And we can just punch that in our calculator. Let's see if I get glare today, always. So we're going to take 34 minus 0.612 times 15, and then times 15 raised to the negative 0.658. So that gives me about 4.178. So f of 15, make sure I got this right, is 4.178. And let's think about what that means. That means that 15 flies would have about 4 offspring per day. Okay, that's what that's saying, that f of 15 equals 4.178. Again, that's the reproduction rate. So that means 15 flies would have about 4 offspring per day. So that's the first thing. Well, the second thing we want to do is actually find f prime of 15. And to find f prime of 15, I'll do that in this color here. We could use the product rule, but notice that one thing you can do is that you can rewrite it just to use, well, I'll say to not use the product rule. All right, and so if we were to do that, I'd have f of p equals, and I would multiply the 34 times p to the negative 0.658, and then I'd multiply negative 0.612p times p to the negative 0.658. We know that when we multiply powers, we're going to add the exponents. So 1 plus negative 0.658 is going to give me a positive 0.342. Maybe I should put a variable though. Here we go. Okay. And that's going to be a little easier for us to differentiate. Okay. So again, now we can use the constant multiple and the power rule. So now we'll use the constant multiple and the power rule. So that means that if I want the derivative f prime of p, that's going to be 34 times negative 0.658 times p to negative 0.658 minus 1. So that's negative 0.658. And then I have minus 0.612. And then now I'll use the power rule here, times 0.342 times p to 0.342 minus 1. So that's going to be negative 0.658. So if I multiply 34 times negative 0.658, that gives me negative 22.372, and then this is going to be a negative exponent, so just for time's sake I'll put this in the denominator. And what about negative 0.612 times negative 0.612 times 0.342? Oh, you can't even see what I'm doing. It's okay, I'm messing it up. Okay, so then that's minus 0.209,304, and then we have another negative exponent, so I'll just put that under here. So p to the 0.658. And so that's my f prime of p. Okay. So now what I would want to do to find f prime of 15 is I would want to put 15 into this expression, which I didn't leave any room to do. So I could have negative 22.372 divided by 15 raised to the 1.658, and then minus 0.209304 divided by 15 raised to the 0.658. I don't know what I'm doing. And that gives me about negative 0.286. And so what that means as far as the units go, if we think about the change in y over change in x, the numerator was the change in offspring, or what was the offspring per female per day. So offspring per female per day. And then down here is going to be the number of flies. So that means that the more flies you put in, that's going to be that rate of change, okay? So that would be the unit, is basically the offspring per female per day per fly. So we can see as we add more flies, notice it's going down at that point. That's kind of the thing. And they're saying it decreases with the number of flies in the bottle. And that's really what that negative rate of change is telling us here, okay? Okay, so we've just done the product rule. So let's talk about the quotient rule, all right? Again, the quotient rule doesn't mean that if you're dividing f and g, you can't just take the derivative of f and then take the derivative of g and then think that you're kosher. That's not going to be good. What we're going to do is the following. d dx of f of x over g of x is going to be, this is a doozy, g of x times f prime of x minus f of x times g prime of x all over g of x squared, okay? Okay, so it's not f prime of x over g prime of x. Okay, this is very bad if you try to do that. Okay, I award you no points. All right, a little, I don't want to say like mnemonic device that people do is this is what they think about for this. They think low d high minus high d low over low squared. Now I understand that that's not anything that we've seen. I mean, I feel like one of the seven dwarfs, like hi ho, no. But anyway, but low d high minus high d low over low squared is often helps students remember all of those different pieces. So say it to yourself every time you do that. You want low, the one on the denominator, times the derivative of the high one, the one in the numerator, minus the one in the numerator, which is, we named it high, and then times the derivative of the low one from the denominator, and then over low squared, over the denominator squared. Okay. Just, again, we're going to use the parentheses and the brackets liberally. That's really recommended for a lot of the differentiation problems so that we can really keep the different pieces separate. One thing to keep in mind is that sometimes rewriting the original function will make taking the derivative easier. Okay, so just keep that in mind, that sometimes we look at the function And sometimes rewriting it is going to be a little bit better, a better plan for us. Okay. In number 6, we're taking the derivative of 5x minus 2 over x squared plus 1. This one we can't really do anything to. It looks pretty good. We can't like split it up because we have 2 terms in the denominator. So we for sure are going to have to use this quotient rule. So the high we're going to look at is 5x minus 2, and the low we're going to look at is x squared plus 1. Okay, so again, we don't start with the high, we start with the low. So we're going to say low d high minus high d low all over low squared. Okay. So now let's take the derivative. I've got the x squared plus 1, and the derivative of 5x minus 2 is just 5 minus. And now I have my high, 5x minus 2, times d low. The derivative of the low is going to be 2x. And then all divided by low squared. And usually if it's like if there's only one factored term, we usually leave it factored, okay? Now in the numerator, we're going to want to combine our like terms, so we are going to distribute in our numerator, okay? So we end up with 5x squared plus 5 minus 10x squared minus, no, just kidding, plus 4x, because we've got minus negative 2, so that's positive 2 times 2x is plus 4x. And then we'll leave this as x squared plus 1 squared. And if I write it in standard form in the numerator, I have negative 5x squared plus 4x plus 5 all over x squared plus 1 squared. And that doesn't look factorable. And there we go. Oh, shoot. Sorry, guys. Okay. I know the problems are too long. All right, so that's how you would attack using the quotient rule. Now, if we look at number 7, oh my gosh, we have a fraction within a fraction. That looks like a hot mess. Why don't we rewrite this to make it a little easier, okay? So let's remove the complex fraction. How can we remove the complex fraction? We want to clear out the x. So we can clear out that x in the denominator of the numerator by multiplying by x over x. And that would give me 3x minus 1 over x squared plus 5x. Okay. That's going to be a little easier for us to deal with as far as the derivative goes. So our y prime is going to be my low, which is now x squared plus 5x, times the derivative of the high one, so the derivative of 3x minus 1 minus high 3x minus 1 d low, so times the derivative of x squared plus 5x, and then all over low squared. Okay. So let's do each of these. X squared plus 5x. Now what is the derivative of 3x minus 1? Why, that's just 3. And now I take 3x minus 1. And what is the derivative of x squared plus 5x? It's just going to be 2x plus 5. And then all over x squared plus 5x squared. P.S. Sometimes I have children try to cancel these. You can't, guys, because that's not a factor. Like, it's a factor of 3, but it's not a factor of the numerator. You know what I'm saying? So we're going to have to flesh out that numerator before we continue. So let's distribute. I get 3x squared plus 15x minus, oh boy, this will give me 6x squared, 15 and 2, plus 13x minus 5, and then all over x squared plus 5x, that quantity squared. So then I want to make sure to distribute this negative. So maybe I'll just do that now to save a little space. So that becomes negative 6x squared, that becomes negative 13x, and that becomes positive 5. So I end up with negative 3x squared plus 2x plus 5 all over x squared plus 5x, that quantity squared. And because the original problem did have a y equals, I'm going to put the y prime in my answer. If I start with an equation, I should end with an equation in that regard. Okay? What about number 8? Oh my gosh, does Mrs. Mackey want you to do the quotient rule, another quotient rule, and then the product rule? Friends, let's try to simplify this a little bit first. Let's think about what we did back in Algebra 2 when we simplified rational expressions. Let's factor and let's cross our fingers and see if anything can cancel out. Let's see also if I can fit this on this paper. Okay, look, I just made it. So I factored my numerators, and I can see that I can cancel, right? I can cancel this z plus 2, and I can cancel this z minus 1. So I have that g of z equals z minus 2 times z plus 1. So that's essentially, it's going to be easier if we multiply it out, right? Z squared minus z minus 2. So that means that if I took the derivative, that would be 2z minus 1 and then minus 0. So that would be my derivative. Now, the issue with happy clouding that as my final answer is that there are some stipulations that are going on. This appears to mean that like everything works, like any value of z could work. However, we have to look back at that original function. In our original function, 1 and negative 2 would have caused the function to be undefined. So when we cancel things out, and it's not evident that those make the function undefined, we should make a note of that, all right? Let's make a note that z cannot be negative 2 or 1. And because it wasn't evident in the function after we canceled, it's not evident in the derivative either, right? But we need to state that. Oops. Okay. Again, we have to state this because it wouldn't be clear from that function itself. So z cannot equal negative 2, there is a negative here, negative 2 and 1. Because those would have made the original function undefined. So therefore, we can't have differentiated those values either, okay? All right, on to example 9. Use the quotient rule and then calculate the derivative at the indicated value. So it wants us to find df d theta when theta is pi thirds, but they don't tell us df d theta, they just tell us f of theta. So we're gonna have to take the derivative. So we have that f of theta is the sine of theta over 1 minus the cosine of theta. So let's try to apply our quotient rule. So that's going to be the first thing is to find f prime of theta. Okay. We're going to take low times the derivative of the high, so d high. And notice that when I have theta, it's not d dx. You see it's d theta. Careful with that. Minus pi d low all over low squared. Okay. Now some of you guys might be over that step. If you're making mistakes, write that step out. If not, and you can jump right to the pieces with the derivatives, that's fine, but just be cautious, okay? So I have 1 minus cosine theta. The derivative of sine theta is just cosine theta minus, and then I have sine theta times the derivative of 1 minus cosine theta. So that would be like 0 minus, and then the derivative of cosine theta is negative sine theta. So that's ends up being positive sine theta. And then of course down here we still have 1 minus cosine theta, that quantity squared. So I guess we could distribute. I have, because there aren't any common factors that I'm seeing here. So this gives me cosine theta minus cosine square theta. I can see this is just sine theta, so this is going to be minus sine square theta. And then this is 1 minus the quantity of 1 minus cosine theta squared. So how could I simplify this? There are a couple things that I might be thinking of here. Remember that we used a double angle formula earlier, but notice that these both have the same sign. So maybe we could factor out a negative from those and get cosine square theta plus sine square theta over 1 minus cosine theta quantity squared. And this isn't the double angle formula, but what is this? That's right, it's our friend the Pythagorean identity. We know that cosine square theta plus sine square theta is just 1. So this is just cosine theta minus 1 over 1 minus the quantity 1 minus cosine theta squared. Oh, I need the squared. Now those are very similar, right? They only differ, like the opposite terms are opposite. So we'll be able to cancel if we can factor something out of that. So if I factor a negative out of the numerator, then I can have the opposite of 1 minus cosine theta over 1 minus cosine theta, that quantity squared. And now I'm able to cancel one of the 1 minus cosine thetas. So my f prime of theta, after all this is said and done, is just negative 1 over 1 minus cosine of theta. Okay. I'm not going to happy cloud it since it's not the final answer, but we did a lot of work, so I'm at least going to put a little something of significance on it. Okay. So then the next thing we can do is evaluate. So now this is asking us to find essentially f prime of pi thirds. Remember that this notation wants us to evaluate df d theta when theta is pi thirds. That's the same as saying f prime of pi thirds. Okay. So it's going to be negative 1 over 1 minus the cosine of pi thirds. So the cosine of pi thirds is 1/2. So that's negative 1 over 1/2. And we know that that would just be negative 2. So f prime of pi thirds would give us negative 2. And that gives us the value of df d theta at pi thirds. Sorry. All right. So there are times that even when we see a quotient, we shouldn't use the quotient rule, that we should use the constant multiple rule instead. Essentially, that's usually when you have one term in your denominator, like we see in example 10. So in example 10, when we find the derivative, I mean, you can use the quotient rule. It's just going to be way more work. what I would do for something like letter A, where I have y equals x squared plus 3x over 6, is to think about this as 1/6 times x squared plus 3x, or you could even, distribute that and think about it as 1/6 x squared plus 1/2 x. It doesn't matter to me. But then at that point, then when you find the derivative, when you find y prime, then you're going to take 1/6, and then essentially you're going to take the derivative of the x squared plus 3x. Okay, so you can pull out the constant and then can go from there. So the derivative of x squared plus 3x is going to be 2x plus 3. So therefore your y prime could be written as 2x plus 3 over 6. Again, maybe you ended up writing it as 1/3 x plus 1/2, like 1/3 x plus 1/2. That's equivalent. That's fine as well. Okay. In letter B, I have y equals 5x to the 4th over 8. Again, yes, this is a quotient, but it might be smarter for us to think about this as 5/8 times x to the 4th. So then if I'm going to find my derivative, y prime or dy dx or whatever you want to call it, then I can take 5/8 and again times the derivative of x to the 4th. What would the derivative of x to the 4th be? Well, that would be 4x cubed. So that ends up being 20x cubed over 8. And if we reduce that, we can divide them by 4. So that gives me 5x cubed over 2. Or I guess you could write it as 5/2 x cubed. Again, those are equivalent, right? Make sure that you know how to manipulate. So your answer might not match exactly, but if it's equivalent and if it's like a decent looking simplified form, you're fine. In letter C, I have y equals -3 times the quantity 3x minus 2x squared all over 7x. And you could use the quotient rule here, but I notice that I have a term in the denominator, so maybe I could simplify that a little bit. So what I could do here is I could distribute in the numerator to get -9x plus 6x squared over 7x. And then I can apply that 7x, I can divide each term by 7x, and that gives me -9/7 plus 6/7 x. Okay, so that means that my derivative here would basically be 0 plus 6/7. So my y prime is 6/7. Always. And I know that we do have when x doesn't equal 0, but do you see how the derivative doesn't involve x? So because the derivative doesn't involve x, we wouldn't need to state anything about that. Okay. And then in letter D, I have y equals 9 over 5x squared. So I could definitely rewrite this one, right? I could rewrite this as 9/5 times x to the -2. That would be nice. And so then I could find my derivative by taking 9/5 and then by taking the derivative of x to the -2. So that's going to be -2 times x to the -3. So my dy dx would be -18 over 5, and then again, get rid of the negative exponents, x cubed. Okay, and you might say, well, do I have to say that x cannot equal 0? That's pretty evident from this, that x cannot equal 0. Okay, so because it's evident in the derivative, then we don't necessarily have to restate it. Okay, we just restate it when we have a derivative where it wouldn't be obvious itself. Okay, one more thing real quick. Now, example 11. This curve, y equals 1 over x squared plus 1, is called the Witch of Agnesi. after the Italian mathematician Maria Agnesi, who wrote one of the first books of calculus. What a smart lady. So the odd name is the result of a mistranslation of the Italian word la versiera, which means that which turns. So because la versiera means that which turns, right? You see how it turns? They accidentally like mistranslated that to mean like which. Interesting, right? So anyway, it wants us to find the equations of the tangent lines in general form at x equals plus or minus 1. Well, now that we have, we can utilize the quotient rule to help us out with this. So we'll be able to do that. So the first thing that we need to find the equation of the tangent lines is we need the slope, right? So for the equation of the tangent lines, the first thing we do is we need the slope. Okay, so y prime is going to be my low, which is x squared plus 1, d high, the derivative of 1, it's a constant, is 1, minus my high, which is 1, d low, so the derivative of x squared plus 1 would be 2x, and then all over low squared. Okay, so I can see that this term totally cancels out, and that y prime is going to be negative 2x over x squared plus 1, that quantity squared. Okay, so that's my slope. Now, it wants the equations of the tangent lines at two places, okay, at x equals positive 1 and at x equals negative 1. So let's find each of those. So let's start at x equals positive 1. So we're going to need to find at x equals 1, what is our slope going to be? Okay, so at x equals 1, the slope is going to be negative 2 times 1 plus 1 squared plus 1, that quantity squared. So that's going to give me negative 2, 1 squared is 1, plus 1 is 2 squared is 4. So that gives me 1/2. And again, remember that that's like my slope. I'll just remind you guys that the derivative is like the slope. Remember to write the equation of the tangent line, not only do you need a slope, but you need a point that goes through the original equation. So we also need when at x is 1, what the value of y is. So we just use the original function, 1 over 1 squared plus 1. So that's going to be at 1/2. Okay. So essentially, what I'm going to do is I want an equation with a slope of that negative 1/2 that goes through the point 1/2, right? So we can use point slope form for that Taylor form. So y minus 1/2 equals negative 1/2 times the quantity x minus 1. So we can distribute y minus 1/2 equals negative 1/2 x plus 1/2. And it does ask us to have it in general form. And remember that general form is when it equals 0. Okay, so we could move everything over and get 1/2 x plus y minus 1 equals 0. And oftentimes general form doesn't have any fractions in it. So I'll multiply by 2 to get x plus 2y minus 2 equals 0. Okay. Now we did that for x equals 1. Note it's also asking for us to do that when x is negative 1. So that's going to be what we do here. So what's going to happen at x equals negative 1? And we follow the same steps. We need our slope, which means we need the value of y prime at negative 1. So negative 2 times negative 1 over negative 1 squared plus 1, that whole quantity squared. So that's going to be -2. Oh no, +2. Negative times negative is a +2. -1 squared is 1 plus 1 is 2 squared is 4. So this time our slope is going to be +1/2. And the actual y value at that point, I'll put, again, -1 in for x. So that's going to be 1/2. So for 3b, I'm going to want an equation with a slope of +1/2, but that goes through -1, +1/2. So I can use the same process. So 1 minus 1/2 equals 1/2 times x plus 1 in point slope form. And then I can distribute and get one side equal to 0. I always like the x term to be positive. And then I'll multiply by 2 to clear all the fractions. Okay. And again, I just did that because it did ask for general form. Okay. So again, if you did write it in slope-intercept form, for example, and got y equals -1/2 x plus 1, or y equals +1/2 x plus 1, those equations are correct. But just make sure you pay attention to detail about the way that they want the answers expressed, okay? And just know how to convert from one to the other, all right? Whew, that was a lot, guys. So I hope you enjoyed learning about the product and quotient rule. We'll be using those lots going forward. So we'll see you next time.